talk. Thank you. So if I can have my slides, I will try to introduce you to the world of glycans, something not many of you do now. But glycans are the additional layer of complexity between gene sequence and a protein function. Because the polypeptide part of a protein is defined by a gene. It doesn't change. It changes very slowly evolutionary. But the glycan part of a protein, and nearly every protein is glycosylated, is encoded by a network of genes, all the epigenetic regulation, all the environmental factors, which come into play to decide what kind of a structure will be attached to the protein and what kind of a function this protein will have. So from the functional aspects, alternative glycosylation, adding a different glycan to the same glycosylation site, is analogous to coding mutation. It can change the structure of a protein, it can kill you. But from informational or evolutional aspect, the glycome composition is a complex trait. It's inherited as a complex trait. It's not monogenic. So this enables diversity without the risk to genetic heritage. But the problem with glycans is that they're complicated. They integrate genetic information, epigenetic information, environment into chemical structures, which are not that easy to quantify. And in addition to being information, these molecules are function. They regulate the immune system. They regulate our immune health. Everything about the immune system is protein glycosylation. Actually, protein glycosylation enabled us to become multicellular. And it's relatively simple molecules, but not easy to quantify because there are many of them. So each glycoprotein can have multiple glycosylation sites, different glycans attached to the same glycosylation site. So it requires a lot of effort to be able to quantify it reliably. And this is something we are working on for 30 years, and we managed to accumulate over 40 million euros of research funding to develop technology which we have today. And then we applied it in collaboration with some of the leading researchers globally, including some of the people being present here, including the Mike Snyder, David Sinclair, and so on, to generate the glycan data, which can be then integrated with other omics data. And we analyzed over 200,000 people. And actually, my lab generated over 80% of the global glycomic output. And now we are putting this data into work to understand many things, including aging, because we were not looking into aging biomarkers. We stumbled onto aging biomarker because we realized that immunoglobulin glycans change a lot with age, which is kind of fun. But even more importantly, the difference between the GlycanAge we calculate from glycans and the chronological age associates with all unhealthy biomarkers, which we know they are biomarkers of unhealthy lifestyle. And this is the research from over a decade ago when we published it initially. Today, we have a commercially available GlycanAge test, which is an easy at-home test, which quantifies glycans attached to immunoglobulin, which integrate genetic information, epigenetic information, and all the health data which is going on. And of course, I'm conflicted here. I'm an inventor and a patent. I'm co-founder of a company. So you have to take my words with a caution, but I can also use my power and give you a discount code. If somebody wants to buy a GlycanAge test, there's a 20% discount. And also GlycanAge came as a sponsor of this conference. So part of the food we are getting is actually paid by the GlycanAge. But there are other people doing it and confirming it. For example, there's a large study done in Qatar. They measured everything which can be purchased on the market, all the proteomics, metabolomics, and glycomics, of course. And when they looked, 9 out of the 20 strongest correlations among everything which can be measured with age were immunoglobulin glycans. The rest of them were mostly sex hormones. But the most important thing about the glycans is they can be reliably quantified. So this is me, my IgG glycan composition, but not analyzed as a single batch. It's analyzed as a sample sent every few months to the lab. And as you can see, there's very little analytical variation. So if there's no biological variation, you get the same number from the lab every few months apart. There's no other omic biomarker which can do that. Most other omic biomarkers will move more just because of analytical variation than what you can expect from biological variation. But you have such a good quantification, and then you see something really going down a little bit, and this is the cardioprotective glycan. This one is predicting heart attack and stroke. And you see this inflammatory one going up, meaning something was going on in me. I had no idea what. So I did a lot of trying to find, and I had a root canal infection I was not aware of. I fixed it, and these biomarkers went back down. So it's really a tool which enables people to individually track their health, to individually track your patients and have effect on a single individual, because other biomarkers, they work on cohorts. It's great. You can see a lot of data when you have 1,000 people, this and there, because then the measurement error kind of gets lost. And these glycans are really predictive of many outcomes. For example, this is a study we did on 27 populations all around the world. They strongly correlate with expected lifespan. They predict mortality on an individual level. This is a study we did with Sarah Hag. Also, we did a study with Riccardo Mariani. He saw a lot of prediction of mortality. We did dozens of different diseases, and in most of the diseases, we see glycans changing in the direction of accelerated aging. So a person with a disease, many different diseases, will have a glycans looking like an older, healthy individuals. And this is actually what we believe it is. It's we are quantifying the functional effectors of low-grade systemic inflammation. We are quantifying immune health in essence, because the glycans change as these inflammatory processes start to develop. And in majority of cases, we see this up to a decade before disease is diagnosed. So glycans start to change much sooner. There are a lot of compensatory mechanisms trying to preserve homeostasis. Once you lose it, then you actually end the disease. And these are very large studies. I don't have time to go into details, but strongly predicting diabetes, cardiovascular events, diabetes, complications, and so on. I'll just show you one example. So we did a large study together with the German branch of EPIC. They collected 27,000 people nearly 30 years ago. We knew who had a heart attack and stroke. We looked into predictive power, and the glycans were as predictive as the entire AHA score. And interestingly, different glycans were predictive in men and women. So we have a sex-specific biomarker for cardiovascular events, published well, but this is one paper. We did replication, nearly exactly the same predictive power, again, different glycans, men and women. And then we did additional 2 replications. So we now have 4 independent cohorts showing really glycans predict heart attack and stroke. And they're modifiable. We can make a decision, change our glycome, and hopefully also decrease the disease risk. We also published a number of studies showing you can change your glycans with physical activity, diet, hormone replacement therapy, and so on. Something which works in everybody is not eating. So everything you did on a coffee break was bad. Less you eat, healthier you will be. But we don't want to do it. So we were looking, we had 1,000 people on a low-calorie diet for 2 months, and then we put them on 5 different maintenance diets. And each of the 5 diets was beneficial to somebody and detrimental to somebody else. We are all different, and we have to find a way how to identify how are we different. We tested a lot of different drugs, which are so-called anti-aging drugs. Tim Spector and I even published Instagram Live about his intervention when he used metformin, and he really decreased his biological age for 11 years in half a year. But when we did the proper placebo-controlled randomized trial, metformin worked only in a single individual entire cohort. So if you're a healthy individual, metformin will most likely not help you. Testosterone will have a positive effect on most of the people. But if you're a diabetic, you have something like 50% chance that the metformin will actually help you. And the same goes for SGLT1 inhibitors and GLP-1 agonists. So people are different, people respond in a different way, and by looking at molecules, we can actually stratify our patients. GlycanAge is working with 1,000 clinics at the moment globally. We have tens of thousands of patients. This is a fun fact we recently published. So people are younger in summer. So we do something in summer to make us younger. We are older in autumn and winter. And to finish my talk, the idea is that we don't wait for the endpoint, point of no return. We are sick. We want to identify biomarkers, monitor the disease development, intervention early, and then prevention of a disease. GlycanAge, which is measuring the immune health, is already in the market. There are other glycan tests being developed by our lab, for example, the total plasma glycome for metabolism and so on. And at the end, we have a large team in my company in Genos who are doing research, and we are doing a translation to the GlycanAge. And I thank you all for your attention.